All right. Can you see my screen, Steve?
Yes.
Okay, let's get started. I'm good. Oh yeah, well, thank you for everyone joining us for November's DataWorks Maryland meetup. Very excited to have Steve Milligan talking about edge device computing with machine learning and deep learning. He's an expert in the area, and we had a dry run a couple days ago, and I think it's going to be an amazing talk. We've never really had a lot of focus on this area, so I think there's a lot that we can learn. Before we get started, I'd like to just go through the intro slides and then some logistics real quick. So we are a sponsored meetup, so we kind of do this every month. But Varen Technologies has supported us for several years. They're a Maryland-based software engineering, data science, system engineering company focused on government contracting. If you're interested in learning more, you can always reach out to me or Varen Technologies directly. Clarity Business Solutions also does a lot of work in the data science area for local agencies in the Maryland area. They also run the MongoDB meetup, which I think they're trying to get a little larger. If you're interested in learning more, please reach out to myself or Clarity directly. ClearEdge, they also are doing work with the intelligence community, a lot in big data, data analytics. So they do some really exciting stuff. If you're interested in learning more, please reach out to ClearEdge or myself. And then Arius Ventures is my company. We're a little smaller, but we also focus in those areas. If you'd like to just chat, just send hi to me. I would love to talk to anybody that's interested in learning more about what we do or what's available in Maryland. So just a couple announcements. Let me just accept this person getting in the room. So I'm still working on getting another event posted in November with FINRA. December, we're probably going to take off. And then in January, we're going to have some interesting talks on malware data science. And then in February on machine learning design patterns. So that's actually an O'Reilly speaker. So that should be pretty interesting. We do have a newsletter if you're interested. I just sent it out. It has interesting articles. There is an upcoming AFCEA event on data science with the government. If you're interested in that, I have a registration link in that newsletter. If you're interested in speaking or working with us, please reach out. I'm always open to ideas. So with that, I'm going to introduce Steve. So Steve is the head of a data analytics financial services practice. He's a certified public accountant, and I think he is basically an expert in IC Agile. I know he's a big proponent of that, and we had some side conversations about some of the opportunities that edge computing grants people to build products quickly, to do some experimentation. And we started discussing various things from the NVIDIA autonomous vehicles to everything. So I think it's going to be a pretty awesome talk. And the last couple of things I would say, if you have questions, I will be monitoring the chat room on both YouTube and Zoom. Depending on the question, I might ask it during. If not, I'll try to curate them and ask at the end. There might be a moment where Steve switches his camera, so you might have to adjust your Zoom settings to use gallery mode depending on how it comes across. But with that, I'm going to hand it over to you, Steve. Feel free to share your slides. I will stop sharing.
Okay, let's. Okay, is everybody seeing slides? Okay, great. The first thing I wanted to do is thank everybody for taking the time to join this meetup today. This is hopefully going to be a bit of a presentation and a discussion. So pop your questions into the chat. But if you really feel passionate, come off mute and let me have it. This is a fast evolving area, and I don't profess to know everything, but hopefully this will be useful. Okay. I wanted to start a little bit about me, just to understand how I got here. Previously, I was an engineer and solution designer for British Telecom for many years. I did the design for the Converge network, the multi-protocol label switch network, and worked in the early days of the internet with MCI, with Network MCI, Vint Cerf and Company. Being a good old Maryland wandering soul, I had to prove to my mother I did more than party in college. So I got an accounting degree and a CPA, and so I was also a controller and director of quality assurance for Sallie Mae. And these days I call myself an agile coach, and that just means that I work with developers and teams trying to find better ways to do things. And the last bit of my intro was what drew me to AI machine learning in the first place was we had a family friend who developed rapid onset Parkinson's disease and was losing the ability to speak. And I thought of a project to try to enhance, determine how much information had to be in an utterance in order for it to be converted back to regular English, and what sort of devices it could be put on that would be small enough for a person to use in the real world. So that's how I got into this whole interest in edge computing. It was how do we take models and move them into the real world and build solutions for people. I just wanted to spend a quick second, because I know when I say I was an agile coach, probably somebody got this picture in their mind and started groaning, oh yeah, this guy's going to talk about user stories, or, I'm old school agile. And as an engineer, I believe that the roots of real agility are people with interests forming their own teams, identifying solutions they want to solve, breaking it down and working it in short cycles. I personally know 4 people who signed that Agile Manifesto. I know they're all engineer developers, and so this is part of the passion that drives me forward. I believe there's a lot of opportunity when we start looking at edge devices for interested parties to form teams. And in a post-COVID world, we're going to need people to build solutions and figure out how to get them out into the real world. So that's what's driving all this. And as from somebody who was according to my mom, I was asking for construction materials when I was 3 years old. I guess that makes me an engineer for life. I've always liked building things. So this discussion is going to be mostly a survey of stuff I own. It is not exhaustive, and participants on this call may have valuable input to make. So please, again, pop in that chat and let's make sure that we get your updates in. Again, my view of building solutions, you find a problem, and it and in this world, in the machine learning AI world, we also look at how we can enhance, algorithms. Can we use parallelization? How can we optimize them? And how can we get it out into the real world? So I stole this slide from somebody. This is just sort of the stock view of, when we're talking about edge, what does it mean? And it's really a umbrella for devices in the real world. That's how I look at it. A lot of model development, because of the size of the data sets, is resident in the core. It's on Azure, it's on AWS or Google Compute. But the edge brings this into reality. So now the scope of this talk. So I put, AWS and GCP and other things. That's where your models are going to get built. I did this talk about a year ago, And when I was updating it for today, I was amazed by how much had changed and how much my thinking on this had changed. So hopefully I can share some of that progression. Recently, Jensen Huang, the CEO of NVIDIA, gave a talk about the edge of the network. And in the thoughts of NVIDIA, the edge of the network was a big NVIDIA EGX compute platform, um, which is designed to reduce the latency to the core. But those devices still cost, they start about $200,000. So it's a little bit over my budget. Next step down are AI-enabled workstations like the NVIDIA DGX platforms that are based on V100s. The price is falling like a rock, but it's still, it's still like $5,000 to get started there. So this talk is not really as focused on those platforms. So I decided to focus on what I call deployment targets, which are things that can be used now to deploy solutions. They can also be used for learning purposes, and they're very valuable there. And I have a lot of them. Like any good geek, I have boxes of plastic containers containing these devices. So this is going to be a somewhat personal survey through this. It's, again, if you're aware of other things, there was no deliberate omission there. I did want to mention, and I see my buddy Neil Tender out there, that there's also the bleeding edge, and this is Neil's area of expertise, and I believe you're giving a talk on it. There are ASICs, which are application-specific devices that are burned onto PCBs, and then there are FPGAs, which are field programmable gate arrays. Right now, for AI and machine learning, I don't think there's a lot of stuff that's deployed on them, but that is the ultimate future, which are purpose-built devices to use our AI and machine learning models. Okay. Pardon me, the small delays are me using my multiple displays here. Here we go. Let's see. Okay, so kind of the ground rules for this. When I got interested, since I was self-funded, I was looking at reasonably priced items. So everything that's discussed today is going to fall between $30 to purchase and at a high of about $700. And it'll be really interesting to see what capabilities you can get for that kind of money. So in these deployment targets, some of the things I'm going to go through today are, of course, single board computers, what I would call phone cards. These are manufactured by people like Qualcomm, and they have basically the same form factor as a cell phone, but can be used for inference. And again, deployment of your solutions. There's the GPUs, which is basically focused around NVIDIA products, and then TPUs, which are hybrid ASIC FPGA solutions developed by Google to do linear algebra. So their device is optimized, and basically you can deploy TensorFlow Lite solutions to these devices. We'll go through some of that. Then there are a host of other AI-enabled devices. It's interesting. A lot of them come out of China. They're a little bit ahead in this area. And so they fall into the kind of their own category because they have accelerators, but they don't fall into the straight NVIDIA or Google models. And then lastly, I wanted to spend a little bit of time. Everybody likes to talk in meetups about, huge models. Let's build the next, BERT and train it on the corpus of Wikipedia or huge models, but there's a lot of space for interested people in very small models. Microcontrollers down to certain even Arduinos can run TensorFlow Lite models. And this creates a lot of space for, again, specific devices that would use your AI ML model and implement it to do useful things, and again, creating entrepreneurial opportunities. And the last one, which I'm not going to really cover, is it is possible to deploy using TensorFlow Lite to JavaScript. So I think some of you have already seen AI-enabled websites. So the thing that's got me really excited is that in moving models to production or into the real world, it creates a lot of space for teams of people with different skill sets. And so if you have a friend like Neil, who's a good electrical engineer, they can help you power manage your project so that your AI device doesn't burn a hole in people's pockets. If you work on an existing team, working with these edge devices can help you understand the financial models of, so when you're building products, you can better prototype and propose new solutions and discuss how much it's going to cost. So first, lessons learned in my journey. Even though some of the devices we're going to look at are very powerful, that base model creation is still a thing for the cloud, for the core. If you're going to build the next BERT and again train it on the a huge corpus, that's where that's going to happen realistically. And I did spend a little bit of time fumbling around, thinking that some of my bigger boxes could do big training, and it was just a lesson learned that these edge devices are mostly targeted at transfer learning, meaning you're going to start with a base model and do something with it. And then there are some emerging areas like federated learning where, and I'll discuss that a little bit more at length. And the big one, of course, is robotics. These devices are the only things right now that are capable of taking a model and allowing you to perform actions in the real world, because they have the interfaces for, input, output, and interacting with physical devices. And again, I hope I'm not restating the obvious, but transfer learning is just a technique where, again, you're going to take a pre-trained model and maybe you're going to retrain it to do something you want. It allows you to avoid the overhead of days, weeks of training and the costs associated with that. And it's an emerging area. There are a lot of models that are available, in open space for this purpose. So, so an example, just a toy example, might be that if you had a model that identified cats and you wanted to retrain it to identify dogs, you're using the weights from the initial model and you're just retraining, and that can be done on these devices quite easily. An emerging area, and I think we've heard about this in other meetups, is the idea of having security through federated learning, where your device downloads a model. Like in a doctor's office, you might have one of these edge devices, and it would be used in a doctor's office, but then the data created, or the updates to the model, would be aggregated and encrypted to anonymize the data, and then could be used to update the base model. I've heard a few talks about this. I have not seen it deployed yet, but again, this is an area for inventive people to to work with these devices. So software for these things, I just wanted to touch on a little bit that most of the your PyTorches and TensorFlows are up at the top of that stack, sitting on top of Python. One other feature of edge devices is they're going to allow you to learn and manipulate things in these lower levels. So you can use languages that are better suited to high performance computing, like C, C++, Fortran, and actually execute them on the device. And again, good learning opportunity. Oops, I think I placed this slide in the wrong place, but I'll touch it right now. So when we get into the devices, they're going to fall into a couple of categories. One which are CPU driven, and the other which is GPU or TPU. And so just a quick graphic to show the difference is that with a CPU, you have a few cores that are capable of performing a lot of operations, but the number of cores is limited. When you move to a GPU, or it's even more linear algebra specific TPU, you have a lot of cores, hundreds of them. They may not be that fast, but because they can execute parallelized computations, you can get a huge speed up by doing them. So I'm going to skip that for a second. So now getting into the devices. The first one I wanted to talk about was was a favorite that pops up was Raspberry Pi and single board computers. These are CPU devices, and what I found is that in practice, because they are relatively low powered, they can be used for inference, but they're better used for learning things. If you want to learn how to program Linux, or in a Linux environment, or get to embedded devices, these are good solutions. But for AI now, they've really been superseded by other platforms. They do have the advantage of being relatively cheap. You can get single board computers from $35 to about 70 or a little bit more. I did not test the Intel NUCs, which are a bit more industrial CPU-based systems. So that's just an admission. So moving into the first class of devices that would be used strictly for AI or machine learning, pushing it into the real world, are TPU devices. And TPUs were developed by Google. They come in two flavors. There's the type that you can use on Google Compute Cloud, which are large core network devices, but Google also produces under their Coral brand a number of edge devices that contain TPUs. And so it starts with this dev board, which is like I guess the simplest way to put it would be a Raspberry Pi for TensorFlow. They're Linux boards. They have similar CPU processors, but they also contain this tensor processing unit. So if you're writing TensorFlow code and you want to deploy it, you can convert it to TensorFlow Lite, which effectively just freezes your model, and then you can deploy it to a device like this. Sorry, I have to keep switching back and forth. So that edge TPU is capable of performing, the 4 trillion operations per second. So for inferencing, I don't have the set up right this second, but if you had film at 60 frames a second, it can do edge detection in real time with that amount of power. For experimentation purposes, Google also makes this as a USB dongle. So it just means that you can easily add it if you have a laptop and you don't have any GPU or TPU and you wanted to play with the TPU, you can always just get that USB dongle and stick that in there. If you're an electrical engineer, they also make smaller form factors, like the actual device is on a mini PCIe card that you could put into a desktop or a laptop if you're handy. And again, how this works is, you would develop your model in TensorFlow, probably on Google Compute Cloud. You'd convert it to TensorFlow Lite, and all of the software required to do this is within the TensorFlow ecosystem. So if you go out on the TensorFlow website, this is a real thing, and you can try it today. And again, for inferencing, for actual doing things in the real world, that 5 tops gives you a good amount of power there. And also, going back to that dev board, you can see that it has the GPIO inputs like a Raspberry Pi, so that if you wanted to do something robotic, if you wanted to use your model to control something in the real world, you have those interfaces to experiment with. So this is a real good solution for people who are trained on TensorFlow or want to learn it. All you have to do is go out to the TensorFlow website, and there's a lot of stuff out there to take you through tutorials, help you build models, and then the sky's the limit from there. And if you have an engineer on your team, I don't think I have a slide here, but a depiction of the actual ASIC that's used for TPUs fits very well on top of a penny. You could probably fit 4 of them on a penny. So this is really, getting to that real world. So again, this slide just shows that if you took a not real high powered CPU and ran a model on it, what the comparative speed up with Google's TPU solution. So you can see that the blue columns are the time it takes to perform the inference with the TPU versus a GPU. So you're getting a huge speed up. And this is for transfer learning models, and you can see some that are probably familiar to many people in this call, like ResNet, and the numbers underneath are showing what size image was used in the inference. Couple of things to mention. One, the Google TPU solutions run a different variant of Linux. It runs Mendel Linux. In practice, I found that it's not difficult. There's not a whole lot of differences between Debian and the Mendel. It's worth mentioning. And the only other thing I'll say is, in their current configurations, the TPUs get hot when you do inference. So this is something for smart folks out there to address, which is power management. You get a lot of computation for a low power input, but again, it's just something to think about when you're designing prototypes. I was talking about the pace of change. When I first gave this talk, the Google Coral devices were just coming out. Now things have progressed to where you can now use multiple TPUs if you have a solution. So you could potentially either use a bigger model or speed it up by having multiple TPU devices, or you could break a solution up sequentially so that TPUs are doing the linear algebra for different portions of your solution. But that's a nice thing, and again, it is covered in superb detail on the Google TensorFlow site.
Hey, Steve.
Sorry.
Hey, I had a question. I was trying to Google some stuff as you were talking because I'm not as familiar with this area, and I saw some references to like Tensor Lite or TensorFlow Lite, and like you have to be compatible with the API. Are you able to talk any? Like I'm only vaguely familiar with like TensorFlow and Jupyter Notebooks and people using the TensorFlow library and that. But can you speak a little bit to like what TensorFlow Lite is and how that's a little different?
Yes, absolutely. Because I had written on my slide, lesson learned. So when you're building your notebook and you're building a model, let's say on the GCP, you're using the full TensorFlow. But once you feel that you have a model that you're ready to deploy, TensorFlow Lite, in my opinion, is one of the worst acronyms because it's not a light version of TensorFlow. And Neil, I can see you down there, so keep me honest. What TensorFlow Lite really is that when you're going to deploy your model, you want to do optimizations. And TensorFlow Lite is the converter that applies those optimizations. So it's going to do things like prune unnecessary branches out of your model. It's going to look at, can you convert floating point to fixed point, or do things that's going to speed up your model. But and the net effect of that is, while you're in TensorFlow, you're making changes. You're tweaking your model. When you go to TensorFlow Lite, it freezes that model for deployment, and that's the big difference.
Yeah, Steve. Hi, Neil here. I think as you mentioned before, the edge devices, that like the edge TPU is it's making the model smaller by doing quantization and pruning. So it's it may not be operating in like complete floating point math. It might be doing fixed point math, for example. And I think when you go from TensorFlow to TensorFlow Lite, this quantization that you're talking about is part of that process.
Yes, thanks, Neil. And the other thing is that unlike the NVIDIA stuff that we're going to look at next, right now Google doesn't let you write code directly to the TPU solutions. Those are proprietary. So what happens is when you're converting to TensorFlow Lite, it's looking at the math you're doing and it's saying, is this a linear algebra solution? And that's when it gets pushed to the TPU. And Jason, I don't know if that helped.
No, it did. No, that was good. There was a question like, any thoughts on the differences between TensorFlow Lite and the full Tensor API? I guess I'm going to reword the question. Is there things that you can do in TensorFlow that aren't transferable to TensorFlow Lite?
And that's why I said I thought TensorFlow Lite was a bad acronym, because it's not like one's TensorFlow Junior. It's you're building things. So like you might have code in TensorFlow for data ingestion, for training. You're not going to need that on an edge device. So what TensorFlow Lite is doing is fixing and optimizing your model for deployment. It's not a cut down version of TensorFlow. And
Okay.
and I think one thing, it's covered very well in the documentation on the Google site. As a matter of fact, if I were going to isolate a problem, I would say there's so much documentation that it takes a while to weed through. But sometimes in TensorFlow Lite, you can do things like you can do part of your transfer learning on the device, and so that's where you might call it a limited version of TensorFlow. But you can kind of eliminate that from your thought path by saying, if I'm going to change the model, I'm just going to go back to TensorFlow. The straightforward way to do it is to see TensorFlow for development of the model, and then TensorFlow Lite is helping you push that model to a production target.
So there was one more question about that, and it was more the person asked, is the conversion to TensorFlow Lite changing the model structure or complexity at all? He thought that it was an optimization, but it kept the TensorFlow structure intact. Does that make sense?
Yes, and I'm also gonna ask for a little bit of help from my buddy Neil there. That when you do quantization, it can change the model, because if you have branches that aren't ever reached, I think it prunes them off.
Yeah, I don't have any really great experience with what Google is doing specifically with the TPU with TensorFlow Lite, but I can say that there's lots of different techniques that are used to try to reduce the size of the model. I mean, the first thing you do is you use fixed point instead of floating point, right? So because floating point math takes more computation power than fixed point math. And it uses a lot more energy as well. So if you can do 8-bit arithmetic instead of 32-bit floating point arithmetic, you save a lot. So that's traditionally done. But when you quantize, you introduce noise in the process. So there's a trade-off between how much quantization you do and how accurate your model is going to be. You lose something when you do that. So there's all kinds of techniques out there to try to get the best bang for your buck. How can you quantize and still maintain a highly accurate model? And then pruning is another technique where you notice some of the weights in your model are really close to zero. So maybe let's just make them zero. And if they're really close to zero and you make them zero, then you don't really lose much there either. It turns out that your performance is still very, very good, maybe almost as good as it was before. But the beautiful thing about a zero is that you don't have to do any computation. You multiply something by zero, you get zero. So those basically don't even have to do those multiplications. So these are techniques that are used. And so I think that generally you don't restructure the whole model. You keep the model as it is, but you can maybe some of the nodes can basically be or some of the weights on some of the nodes don't actually have to be computed, and they don't even have to be stored. You can have the model stored in such a way that it's smaller, because a lot of the weights are maybe more sparse. A lot of the weights are zeros, and the weights themselves are not floating point. They may be 8-bit or some. There are some that go all the way down to 4 bits, 2 bits. There's even research on single bit weights and activations. So that's, I think, what's typically done.
Thanks for that, Neil. Yeah, and Jason, a little bit of clarification. Within TensorFlow Lite, there are some parameters you can set to try to, as Neil was saying, control any loss of accuracy versus performance gain. And this is analogous to, so this is all within Google's ecosystem. We're going to talk about NVIDIA in a moment, and people may be familiar with, NVIDIA has a process called TensorRT, which is its optimization phase after you build a model. So these are sort of comparable solutions. And what it comes down to is what you have to do between, again, building your model, with big data in the cloud and getting it out to where, you can do something in the field,
That's fine. Yeah, I'll let you move on. I will say one last thing though. I did a quick search and it looks like the devices went on sale and they sold out pretty quickly. So I don't know how easy it is to get one of the Coral devices right now, and they look pretty popular.
Yeah, I was going to say as a side note, just to show how fast this is going. Yeah, a lot of things like when we're going to get to the NVIDIA platforms, you'll see a lot of them are sold out. But my tip is to go straight to the NVIDIA site and try to buy it from NVIDIA. So I've been pretty successful there. Okay, so I think I had that slide up before, but now we're moving to the next phase. Probably the hottest products in this edge space right now are coming from NVIDIA. And a lot of it just has to do with their size and scope. But interestingly, NVIDIA just recently bought ARM. And the belief is that a lot of technology is going to move that direction because Apple has announced they're going to standardize their products on ARM architecture. And so I don't want to use the word loser, but the people who stand to suffer market share is probably going to be more in the Intel space because they're tied to Windows and it's just a separate architecture. But anyway, the next set of devices that we're going to talk about have built-in GPUs, and they have a whole ecosystem built by NVIDIA. So let me start with one that people may be familiar with. There's this Jetson Nano, and it's about the same size as a Raspberry Pi, but the difference is that this device has a GPU built into it. For people who have worked with NVIDIA products before, one caution I'm going to throw out right from the beginning is NVIDIA devices are rated by what's called compute capacity, and this is a compute capacity 5. So a lot of software will run on it. I'm going to talk about some containers that are available from NVIDIA that help you set things up almost instantly. Just watch your space because a few of them won't run because there's not enough processor capability. But this little device for $100 gives you 128 of those CUDA cores. Trying to figure out how to go backwards here. Oops. So you can think of these rows on this GPU depiction on here on the right to be like the CUDA cores. And so just in comparison, like a 4-core Raspberry Pi has 4 cores. This effectively has 128. It also has CPU, a quad-core CPU on there, so you can write code that utilizes both CPU and GPU. So as a learning platform, this is really excellent. NVIDIA has recently expanded the line here. So the one I'm showing has 4 gig of RAM on it, of GPU RAM. The other ones, the latest ones have 2 gig and only cost $50. So if you're just trying to learn, get your head around GPU, CPU, what's the difference, this is a good place to look. But moving swiftly along, the next step, this was actually an earlier dev kit from NVIDIA, which was their TX2. The TX2 has about 4 times the capacity of that Jetson Nano, but significantly, NVIDIA sells the base boards for TX2s in an industrialized format. So if you were building a solution and you really wanted to sell it, this would probably be the first place you would start in terms of sizing, because it comes in, you can get the industrial version. And so you can see that it has 256 GPU cores, little beefier processors. I think I have the price wrong there. I think it's probably about $300 now. But I'm not going to spend a lot of time on the TX2 because, I put these in the wrong order. But the biggest Jetson, now this costs about $700. But I thought about my first PC that I bought way back when, and I probably paid $3,000 for it. So this is a bargain. NVIDIA also sells these in pairs under what they call their drive kit. So 2 of these are what you need to run a Tesla or an autonomous truck. This is the industrial platform design for the real world. You have a relatively huge amount of power. You have 8 CPU cores, but notably you have a NVIDIA Volta class. So this is a compute category, compute capacity 7 GPU. So if you're at a university and it's telling you you're using like Volta class or compute capacity 7, this is it in a little box that you can own for yourself. It's got a lot of power, and you can see that this one has the tensor cores. And what those are is these are the analogs to Google's TPU. So if you have, if you're performing functions where you're doing a lot of linear algebra, you're doing matrix math, the tensor cores are optimized to do that processing, and will do it even faster than just the general purpose GPU. I should have had this one in order because I was going from smallest to largest. But the latest and greatest thing from NVIDIA is this Jetson Xavier NX. It has a little bit less GPU RAM than the Xavier, but it's the same form factor as a Raspberry Pi. This costs about $400, but if you're building a team and you're building real products, this is a sweet spot in terms of what it can do. You have a 6-core CPU, you have the 384 CUDA cores and the tensor cores. So, and significantly, you have that GPIO like a Raspberry Pi. So if you're trying to interact, you're building robotics, or you're working on your own version of a self-driving car, you need to have those interfaces so you can interact with other devices, right? Your control structures. So all of that's there for you. And so both of these Xaviers are designed for to power robotics and embedded devices, and to run multiple ML, AI type of models, and then have them interact with the real world. So I wanted to show, this is a little bit of a busy slide, but what it shows is what you can do with various different devices. And if you notice through this column here, now these two at the bottom have been sunset, and you don't see the nano on there. But you can see over here on the left column, NVIDIA compute capabilities. And if you get a hold of an NVIDIA card, in a workstation, you can always just look, easiest thing to do is look it up on the NVIDIA website, what the compute capability is. And what you can see when you get to this Volta architecture, this 7, right now the latest and greatest from NVIDIA are the Ampere cards. Their compute capacity 8, but 7 is a lot of muscle. And you can use this not only with high-level abstractions like PyTorch or TensorFlow, but you can actually go in and write code, native code in C, C++, Fortran. You can use directives like OpenACC, which are basically telling the compiler to parallelize, code without, basically changing the code. And it gives you access. This is a little bit upside down. It gives you access to libraries that NVIDIA has created that for specialized high performance computing. And there are a lot of models that are just out there, but you don't have to reinvent the wheel. And by the way, so like the CUDNN is a library optimized for neural networks. The FFT is for fast Fourier transforms. And there's a lot of different math libraries that are out there that you can learn and you can use on these devices. And I wanted to take just a minute. This is a little bit of a diversion, but so why do you want to learn about GPUs versus CPUs? But it depends on the type of problem you're trying to solve, because so I'll just throw out a quick question to you. If you're looking at these two different things, one is a set of fully connected layers in a neural net, and the other are functions within that. So like your loss form, your ReLU, or just implementing dropout. Which one do you think is more math intensive? And I'll just move quickly to the answer is, of course, if you have a bunch of fully connected layers, you're doing a lot of math. And so this is what you want a GPU for. This is, and if it's really dependent, it'll benefit from having these tensor cores or a TPU type of solution, in the Google ecosystem, because it's helping you do math quicker. These devices will also help you learn how to effectively manage memory, because what happens is with GPU, TPU type devices, they can do math so fast that your challenge becomes not starving the processors. How do you get the data in from memory? So that's why they're called memory limited steps. But these are all good devices to learn how to work with that. And this is just, I won't spend a lot of time on this slide, but it's just showing that, from a learning perspective, what you can do with any of these GPU type devices, you can write code on the left-hand side. This is just sort of modern C++ and Fortran, which have keywords in there that allow you to do concurrency. So you can see like where it says do concurrent and the double colon up there. Those are just language constructs, and the devices, if you're using the GPU accelerated compiler, it's that easy to get concurrent. The next level over, if you've heard of things like OpenACC, these are compiler directives where you can go into your code and say, okay, I'm going to do some matrix operations here, and what I want the compiler to try to do is to optimize that. So that's how that's done. And then over on the right, you're seeing straight CUDA code. And this is if you want to write your own kernels, and you can see that notably where it says block index and dimensions, that's allowing you to manipulate directly the blocks inside the CUDA cores and threads inside those blocks. And I think this was written, this example might have been done with an older version, because it's showing these memory copies in C, but there's actually CUDA managed memory, which allows you to share memory between CPUs and GPUs without moving it. So if you're really trying to come up with an intense solution, you can execute these kernels, which will perform your linear algebra, and then just pack those in with regular procedural CPU code. So that was a mouthful, wasn't it? Now, how about let's do things the easy way? So NVIDIA has started their own library and of containers that you can simply download the container and run it on one of these devices. And it's, I'll try a live demo at the end, if time permitting, but it's really like a 2-click solution. Let me switch my share here. Okay, so now is everybody seeing the NVIDIA screen?
Yes, I am.
Okay, so this is this NGC catalog. And I just wanted to show you that if you've ever tried to configure software on your machine, I find that to be a supremely aggravating activity sometimes, and especially when you're trying to resolve dependencies and make sure you have the right version of a bunch of different software. Well, for instance, if you want to use TensorFlow, PyTorch, Jupyter Notebooks, and a bunch of things, it's as simple as in this solution, you just pull this container and onto your device, and you just do, Docker run, and it's there for you. And the great thing about using these containers is that if you're in the early stages of learning, and you're like me, you're going to screw things up. If you pull a Docker container and then you just sort of power off one of these edge devices, it goes away. So you can't, make too much of a mess. So it's good if you're not comfortable configuring software on Linux systems. You can look through these libraries, and there are containers, and then there are also just raw models, and you can see things like, BERT large, and any of those NVIDIA Xaviers will run any of the models that are in this library. And it's worth a try to run it on a Jetson, because a lot of them will run there. So let me switch the screen back. And again, there are lots and lots of models here, and there's also a website called Jetson Zoo that lists in tabular format, different models that you can simply download the container and run them, or you can download the model if you like to do it that way, download it into PyTorch, TensorFlow, and away you go. So this is a big change over the year. When I first started buying these devices, there was a lot of configure it yourself, and now the world seems to be moving towards containerization, and this also helps if you get used to working with containers, because if you were going to deploy, you come up with the world's greatest solution and you want to deploy it in thousands of places, if you can create a container, then your Kubernetes or Docker Swarm systems will work on it without any other modifications. So do we want to pause here to see if there's any questions or comments?
I'm monitoring this stuff. There hasn't been any questions, but if folks want to type them in, I can start capturing them. I had a quick question, because you talked about the Coral and then you talked about the NVIDIA. Is there a clear leader in this area? Seems like NVIDIA, you focus a little more on them.
Well, I think this is my opinion, but I think NVIDIA is in the lead right now because they are the builder of AI-enabled GPUs. So anybody who's doing GPU is using NVIDIA stuff right now. But this is not to discount Google and the approaches are a little bit more different. If you're using NVIDIA stuff, hopefully what you're seeing is there's a lot of opportunities for do it yourself. You can get in there and fiddle around close to the iron. Google is using a little higher abstraction that says use our software, and this will facilitate using these built for purpose devices. I think Google, from their documentation and training materials, may have a little lead in that space. But again, this is emergent stuff.
So what
And
area?
Everybody's opinion is equally valid.
So for for folks that want to get involved in this area, what do you think's more easy, like an easier path? Do you think to go down the NVIDIA path, or to go down to the Google Coral, or look at something else?
Oh, good question. I think that if you're interested in business space right now, it's probably going to be NVIDIA, because again, NVIDIA products are used right now heavily in robotics. So, if you want to work in autonomous vehicles, factory spaces, things like that, I'd invest a lot of time, in that space. But that's connection to the physical world. I would say, again, in my experience, which is limited, Google is also really strong, obviously, in terms of, building core-based APIs, and because they have robust support for things like running TensorFlow Lite models in JavaScript, that if your target is websites or web-based, I would probably go with the Google stack.
There's no.
And one more thing to say, that Google has in beta TensorFlow for Swift, and Swift is the software language that replaced Objective-C Apple. So, you know, if you were interested in writing like Apple apps, you know, in the future that were machine learning or AI enabled, you know, there's a good chance they're going to be in TensorFlow for Swift.
Okay.
And I realize I
Oh,
said a mouthful there, but
oh, that's fine. There's no other questions right now. If you wanted to keep on going, Steve.
okay, yeah, let me. Okay, so the next space is so Jason, that was a good leading question. So if Google is leading on, let's call it API based, web based solutions, and NVIDIA is leading in industrial, you know, robotic solutions, and also high performance computing. There's another space we haven't looked at, and that's deployment to the equivalent of phones or mobile devices that you might have in your pocket. And there is support within the existing TensorFlow for Android-based boards. And early on, when I was doing that home nerd thing, I got a hold of, so Qualcomm makes a board called a Dragon board, and the form factor is it's about the same size if you took the connectors off of it of a cell phone, and it has Qualcomm processors, and it has things like a GPU in there, so it's like a phone. You know, you can actually load a SIM in it. And so this would be the type of device you would want to play around with, and probably in using that Google, the TensorFlow ecosystem. If you were building something that would either go in a phone or be in that same sort of form factor, so something you could carry around, do inference on, you know, implement your solution there. And when it first came out, the thing I struggled with was there wasn't a robust Android SDK for AI machine learning. Now there is, and again, it's under TensorFlow on the Google site. So just looking at this Dragon board, for example, it'll happily run Linux or Android. So you know, you can decide how you'd like to configure your solution. And again, it has some advanced features because it has, again, a GPS on the board itself. So, you know, if you were doing something where you wanted to, you know, take advantage of positioning, this would be a good target. You know, reasonably priced, starts about $75, and the 410 is a little bit older technology, but it's good for learning. There are a couple more advanced boards available from Qualcomm, but I don't know. One that I wanted to mention, in a hybrid solution, this CUDA board. This was a very robust single board computer that also dual boots Android and Linux out of China. And I haven't noticed our friend G from Blue Cross on today, but I stepped on my toes. I asked early on, the early drawback to devices like this was it's very powerful. It has a built-in device that's like the Google TPU, and it actually outperforms it. They're calling it an NPU, And if the Google does 4 tops, this one does 5. The tricky part about this when I first got it was the best documentation was in Chinese. So unless you have a friend who can, who could read the documentation, the English documentation was a little bit of a struggle. They've since rectified that. But this is great if you're looking for just a small form factor device that can do a lot of different things. This has extension boards so that I was able to mount a full-sized SSD on it. And it comes with Wi-Fi and Bluetooth built in. It's very capable. And again, in terms of its ability to perform inference, it's a powerful device, and it has those GPIO extensions that would let you, execute robotic functions or, whatever you need to do. Since I'm just doing a survey of stuff I own, I'll mention that when I worked for Ericsson, we used Beagle boards. They were good for training people who are developing embedded software. A lot of engineers who build device drivers or any device-specific code, embedded code, have learned to use Beagle boards. They built this AI board that has a coprocessor, again, like a TPU or the CUDA board. But I have to be honest and tell you, they didn't do a good job of power management on this board. And so I got it to work, but it gets so hot that I had to take an external, like a room fan, and point it at the board. Otherwise it resets itself. But it was a good lesson learned that, when you're building your product, to really consider, that power management and how you're going to dissipate any heat that you generate. So I won't spend time on that. Oh, and here's my TensorFlow Lite slide that I think we already went over this, but it's basically saying that it's not a light version of TensorFlow. They should probably call it TensorFlow Deploy or something. Might be better. But here's a quick summary of what it does. After you've done whatever training or transfer learning, the TensorFlow Lite converts it, and then does the optimizations for deployment. And I didn't put the software slide in, but in NVIDIA, if you look on their websites, you'll see a lot of references to TensorRT, which is the analog for NVIDIA. So it's the optimizations, and they tend to be device specific, that are run to optimize models for inference and get rid of extraneous stuff that's just going to cost you power and not really give you any more bang for the buck. Now I'm down into the last bit of stuff. When I first started doing this presentation, Intel had a solution, this compute stick. And the idea there was that you were going to, it's a USB coprocessor that you could stick into your laptop, or you could stick into even a Raspberry Pi, and perform linear algebra. They still have this. You can still buy one. But what's interesting is that Intel is swinging, in my opinion, more towards FPGAs and ultimately ASICs. But I think they're going to a more engineering heavy solution that says people are going to build for purpose devices. So my only comments about this neural compute stick is, if you're in engineering school and you want to do something that's hard, like everything else in engineering school, get one of these and it will be hard. But it is useful to watch that NVIDIA seems to be, I'm sorry, Intel seems to be trying to make development on FPGA, field programmable gate arrays, easier. So I think their belief is that in the future, we'll have devices that are dedicated to solutions, and they're strong in that space. And this just sort of is a brief overview of their ecosystem. It's engineering heavy. They do have this toolkit, but I would recommend this to, like, electrical engineering students or people who want to build something where you don't have to worry about somebody copying your software and creating a similar device. These are you're going to end up with for-purpose devices here. And lastly, really, I just wanted to briefly just go over two little things. One are small devices. What I've noticed is everybody in AI and machine learning loves a big model. We can't talk enough about BERT, or how big of a training set we have. But there are a lot of solutions that don't need a lot of horsepower, but may be really useful. I know of such grandiose inventions of my own, was like trying to come up with a add-on to my Ring camera that would detect if the neighbor's dogs were pooping in my front yard, and just play a tone or something to kind of break that up. Devices like the Raspberry Pi Zero and just microcontrollers allow for that. They're supported in TensorFlow, in the TensorFlow ecosystem as is. So I guess, Jason, now I'm swinging towards Google, but you can write applications and probably come up with a lot of useful stuff. Imagine a doorbell, like one of those Ring doorbells that recognizes you and unlocks the door if it sees you, and if it's anybody else or it's not sure, door stays locked. So I think this is an area that you don't hear discussed a lot, but probably has a lot of leg room to go. And the last thing I wanted to just mention, this is just for fun, was, of course, everything I've tried has not worked out exactly as planned. There are a couple little things to avoid. Famously, the device that got me started on my interest to edge devices, in 2015, I pre-ordered from Amazon this thing called Amazon Deep Lens. I've never actually got it to work, but I've learned a few lessons, like never buy anything in a sealed case unless you want to break it open.
Why couldn't you get it to work? I'm curious.
And again, I'm trying to be funny or not accidentally flame anybody. But what happened was when Amazon first came out with this idea, they of course required you to work through their ecosystem. So you had to do a lot of things that would allow you to deploy a model from AWS environment into this device. And so you were configuring all kinds of tunnels and SageMaker, and you know, you needed 3 different Amazon accounts. And they pulled this model, I think, because people were, early experimenters were having problems. And then what's happened since then, if you look at Google or NVIDIA, they have managed to make the learning process a lot more straightforward. So, I'll give credit to Amazon for trying to bring this to the people early on. But the lesson learned there was, if it's not, if you can't access it, like even though this runs Linux, they did something to it to prevent you from just using apt updates. So it got into a kind of a race situation where we'd say, I couldn't update certain software because I couldn't update the dependencies that, I could go into Linux and, do what I needed, but then I would just get blocked. It would just say, here's an unmet dependency. And when I tried to load it, they disabled something to prevent that from happening. But again, this was early days. So I'll give Amazon credit for getting me excited, because I thought, oh, you can get this box. It's got a built-in camera. We'll be up and running in no time. Well, 6 years later, I'm just admitting that everything I touch doesn't turn to gold, but maybe there's a lesson in there. And then famously, a couple of years ago, Google had one of their AI summits, and they gave everybody that came to it this little Spark Fun device that it would just recognize the difference between saying yes and no. And like 50% of them didn't work. But the reason I included this in the presentation is that while some things may be harder to work with or appear to be, not as good as advertised initially, both of these devices that are showing up on that slide, time has caught up. So there's the Grove board. If you're into sensors and like you want to have a smart garden or something like that, that's a perfectly fine solution, and it costs under $30. And again, the really tiny little boards like that SparkFun board, maybe you're building a solution where you just want to have the ability for it to recognize 3 or 4 words, and then you're going to drive some other process from it. So as a positive note, I'll say, if you find something and it's not a great solution today, things are changing so fast that it may be a great solution tomorrow. And that takes me to the end of the presentation part. I'd be interested in any feedback or thoughts.
Well, we have just a few minutes. I had a couple questions, and if anyone has anything they want to type in the chat room, I'll grab them. I was curious as to what you think are some of the biggest challenges facing edge computing and machine learning on edge devices.
I think probably one of the biggest challenges, and you've pointed out with questions, are, it's uncertain at this point in time, what solution is going to be employed in any particular case. So, you need to decide where you'd like to invest your time, what turns you on. But I think that's also the opportunity. You can try these out. It's not, these aren't break the bank type of devices. And so I'm, I go back to my initial hope that, people coming into technology now will just like happened with the internet, that we'll be able to use these to devise solutions and products that we hadn't even contemplated and move us away from a centralized model.
Do you see 5G and Internet of Device or IoT? Do you see that changing anything? Actually, I was asking this, but there was another question. Do you see there being security challenges in edge computing with multiple sensors?
Yes, potentially. So let me answer the first question first. And since he's not on the call, I can even out my brother. So a good example, I got a call from my brother. I won't say who he works for, but it's defense related. And he was saying he had been dispatched to find solutions for 5G, because right now 5G may be an answer looking for a problem, right? You're going to have all these high-speed data streams, and you're going to generate a little bit of radiation to do that. But what problem are you solving? So we actually had this discussion, and it turned into an edge computing discussion, because we said, well, if we could get some groups of students, like grad students or whatever, and get them some of these, more powerful platforms that are capable of ingesting that data and doing computation, this is how those solutions are going to have to be developed. Because effectively 5G is just a fast pipe, right?
What about the second question with security? And I guess I'm going to put something else with that question. In addition to security, are there privacy concerns related to edge computing?
Well, good points. So right now, so at the big level, in that first diagram I drew with the that showed the NVIDIA EGX platform, all of that stuff is highly encrypted for communication purposes. But as you move to the edge, you're right. You have to explicitly implement either encryption if you're going to transmit sensitive data, or there needs to be more implementation of federated learning, which says I'm going to aggregate and anonymize data before it's transmitted. But it's early days. I haven't seen in the field, a federated learning application. I know they were talking about it for COVID, like that was supposed to be the app that Apple was developing, where if you walked by somebody, it would tell you what your COVID risk was or if you'd been exposed. But I don't believe that ever got deployed. But again, this is the same as early days in the internet. At first, early days we used to send everything, unencrypted packets, right? Now you do HTTPS, and that encryption overhead is transparent. So it took a while for the equipment to catch up to where you could just run HTTPS, right? I think the same thing is going to happen with edge computing for AI, and 5G has protocol elements built into it to facilitate line speed encryption.
Okay. So there was is there any concept of a zero trust model for the sensors or the edge computing devices?
Yeah, that's my understanding of essentially what federated learning is, right? That you're able to process data in such a way that when you transmit it, there's not a concern about its source or veracity. you're on mute.
So this one's a little different than the edge computing, but there was a question kind of just about, I mean, you seem like a tinkerer, seem like you are following what's going on. You've experimented a lot. So have you, I'm going to put, this is a two-part question. So
Sure.
first, do you have any like thoughts on like the developer experience on things like AWS, Google Cloud? And do you have any thoughts on managed AI services like recognition or comprehend versus the roll your own? That was one person asked that question.
Yes, I mean, I think that that looking at like, you know, development on the cloud is great because it gives you fast access to learning opportunities and the opportunity to build models. You know, Jason, you made a good point that, you know, you said I come across as a tinkerer, right? Well, I also worked for BT Labs and the old Bell Labs for many years, and this is how things were created. You know, it wasn't like some management person came in with a piece of paper and said, you know, go build one of these. It was a bunch of people sitting around, sort of brainstorming ideas and trying things out. And I feel like, you know, for a lot of reasons, probably mostly financial, maybe we've lost a little bit of that. So it's so my response is kind of, to me, the edge is an extension of, you know, the cloud has given us the opportunity to learn and to have access to the facilities you need to build models. And now we need to take that next step and, you know, pack them into some products.
So related to the tinkerer question, there was a question: Have you actually tried to do run any models on your mobile device? Actually, Neil said that he believes the latest Qualcomm chips have a tensor accelerator built in.
Yeah, I've run models on all these things.
On a phone?
Oh, on a phone.
Yeah, phone or a tablet. Yeah.
Um, other than running it on the Qualcomm board, no. But Jason, let me repeat what I said earlier, that in terms of rapid expansion of capabilities, this was a hard thing to do until Google expanded TensorFlow Lite into those types of devices. Now that's not a hard problem. You just use the Android SDK and you know, convert your model to TensorFlow Lite, and it'll run on Android.
That makes sense. Oh, well, go ahead, Steve. Go ahead. You have more?
Yeah, no, I was just going to repeat that warning about then you have to make sure that it doesn't heat up on you. You know.
Yeah.
Get a hot pocket out of it.
So we're running over a little. I think I'm going to wrap it up, but I always like to ask this question because everyone always likes to ask this question. Like, you kind of alluded to like getting started and, you know, some of the low cost and, you know, all the documentation. I guess, is there other resources that you would suggest? I mean, if you went over a lot of devices, if you had to pick one thing, if someone came to you and was like, I want to get started, give me the next step I should do, what would you recommend?
I would say look at one of the base boards, like either the Google Coral Dev board, you know, or the Jetson Nano. They're good places to start. And if you know, and if you're not really excited, you haven't spent a lot of money. I'll also point out that before COVID hit, I used to run under the Bethesda AI group. We actually had an edge compute group. I mean, we still do. And I would bring in my devices, and the idea was to have some workshops and let people get hands-on. So if anybody's interested in that sort of thing, you know, you can just hit me up on email, because, you know, looking forward to getting that going again.
Yeah. So the video will be available. If you want to send your slides, Steve, we can put it up.
Yeah, sure. I'll send you that.
Okay. And then was your email at the beginning of the video or
Yes.
Okay, great. So I know there was a couple other things that seem to come in. I don't want this to go too long. So if you have other questions, I would definitely say reach out to Steven. It sounds like he's more than willing to have a discussion. I think he thrives on that and enjoys having those discussions, it seems like. So again, I thank everyone for joining us. Thank you, Steven. This was really interesting. I actually had no idea there were so many different devices. I always hear about the NVIDIA, but some of the other ones were really interesting to see. Maybe, you can tell us more about your experiments, in a couple months, a year, if you start tinkering a little more. But thank you. And I hope everyone has a good day, and see you at the next meetup, I think.
Yeah, thank you, Jason. And let's get together and build some things.
Yeah, thank you. All right. Have a good weekend, Steven. Have a good weekend, everyone. Bye.
Okay.